Thank you very much. Yeah, as you said, I recently moved to Dresden, but the work that I showed today is done at TU Delft. And it's a series of master thesis projects that we have been running, looking at thin glass and how you could apply it in the architectural domain. These are concepts, so it's not realized. I just want to point that out. But I think it's interesting concept to show you today. So the basic idea is, of course, to take the thin glass as we see it on the devices and apply it in the building industry. Benefit of that would be that you have a more lightweight construction, as also pointed out by Marco in the previous presentation, because it's thinner material. It's about, let's say, roughly speaking, 10 times stronger than normal window glass, and can easily flex it because it's very thin and very strong. So using these three, let's say, benefits, we are looking what we can do with this kind of material. First, we started just out of curiosity to test some pieces of glass. This is 2 millimeter thick glass, about 80 centimeter long. And we are simply bending it in some sort of column bending test. And then we can bend it quite far. Chemically strengthened Leoflex from AGC. And you see that we build up quite a lot of energy now, so that when it fails in the end, it really fragments in small pieces, as also pointed out in the previous presentation. So it's not a fracture pattern from the chemical strengthening itself, but really from the energy that you put into the glass by bending it. We did it with some strain gauges on the glass. So we measured the strain on the glass, from which you can calculate the stress that acts on the glass. And we reached about 500 megapascals. I have to say that this is not the ultimate strength of the glass, because in these tests that we have been running, in the end, the failure comes from this point. If we pass the 90 degrees angles, then there's too much stress at the supports, let's say, at the brackets there, and then it fails from there. You cannot see it, but with a slow motion, we were able to see that. So we can even overpass this value of 500 megapascals in testing. So just to show how flexible it is and how strong it is in the end. So with that, we thought, okay, what can we do with it? And today I would like to show you two concepts that we have explored. The first one is adaptive concept. So making use of the glass to be able to bend it repetitively in a facade construction. So it's not a static system, but a dynamic system that you could adjust. Perhaps you can use that for a double skin facade that you can open up for ventilation. Perhaps you can include some PV panels or PV foils, let's say, to orientate your PV cell optimized to the sun direction. These are just some concepts that we had in mind. So what you see here is the first rendering at the right of one of our students that have looked into that. He also looked at, okay, what can we then, how can we shape this? All kinds of different suggestions given here. Some are realistic, some are perhaps a bit less realistic, but it's nice to do a short brainstorm, of course, of what you could envision to do with this glass. The main question is actually, so how do we actuate this kind of thin glass adaptive facades? And I would like to show you three options that we have briefly explored. The first one is a mechanical actuation. So a student looked at, okay, what can we do with, let's say, simple linear motors, simple linear actuators from the, for instance, greenhouse industry, or from simple movable windows that you can open up. And how can we then actuate the glass? So he thought about this simple system. And if you actuate it differently at the top and the bottom, then you can also some sort of twist the glass, of course. So he made this small mock-up, about 0.5 millimeter thick glass, I think. It's again Leoflex from AGC, chemically strength, 2 millimeters, sorry, my fault. And he simply makes a linear motor actuation at the top and the bottom just to push the window outwards to open it up. I think he went up to about 12 centimeter and a stress of about 400 megapascals. In practice, this would be too high, of course, because then you are getting nearer to the limit. But it's a nice first idea of what you could do with this kind of glass. And then you can make perhaps this double skin facade. So you have a regular skin here, but and then a movable adaptive skin on the outside there, which is then less insulating sensitive. The second option that we explored was pneumatic actuation. So what can we do with pneumatic actuators like this? So looking at soft robotics, soft pneumatic actuators, like these grippers that you can see on in the video. These are just a series of air chambers, let's say, not by us, but by others, that if you inflate them, they can actuate some movement and some grip. Perhaps for this kind of grippers or some sort of exoskeleton applications. So having this in mind, another student looked at, okay, what can we do with that? Oh, sorry, this is just some more examples of this kind of creatures that you can create with this inflatable soft rubber or silicon. And using that, he thought, okay, let's make a system in which you can bend the glass by inflating items, inflating soft pneumatic actuators. So all kinds of concepts. So this is mainly the a series of air chambers that if you inflate it, the glass will bend, perhaps like this or in any other form. So we started off with a very simple first mock-up in the video. This is a folded bicycle tire, an inner bicycle tire. So if you fold it, then you can create this kind of air chambers, balloons, that if you inflate them, they will push each other and then bend open the glass. In this case, it's still plastic, and it's still, okay, it can be looking better, to be honest, but it's a nice first try, of course, of a demonstration of what you could do with it. And then on this side, he made a first sketch of how such a window could look by integrating the air chambers in the edge of the glass. This is he also did some simulations about that. So this is the air chambers. You see a thicker wall thickness here and a thin there, so that if you inflate it, they start to act force. And you can imagine that if you glue glass here, thin glass, or there, or both sides, that you can make a movable structure there. So there was Kongri Za. He was Ojrin was in China, so he went back to China and was able to make this kind of molds with a company there, and then made this kind of rubber air chambers that they welded together after that. And by inflating this soft rubber, you can see that there, you can see that it extends there as a balloon, and then if you make a series, then you can make this compression force, or bending actually. So this is the system again. A system, a series of air chambers connected by some small tubes, and then you can integrate it like this in a facade system, window system. If you want to do that for an insulating glass panel, then it's of course challenging how the edge spacer will accommodate this movement. So as a first step, we thought about, okay, let's use this super spacer, very flexible foam spacer from EdgeTech, so that it can easily follow the movements of the thin glass. So we used that to make a very small mock-up. Here you can see it from the top, 2 layers of glass on the outside, then the flexible spacer in the middle there, and then this is the series of air chambers with the tubes connecting it to be able to inflate it. I have to admit, at this point, we didn't apply any extra sealant or extra glue there, let's say, so no structural interaction further there. But nicely he made this first mock-up. So this is actually glass, thin glass, with the edge spacer there, and then if you inflate these chambers with a simple bicycle pump, then it starts to bend the glass. Unfortunately, in this case, the system was a bit leaking, so we cannot bend it as far as was imagined. But still, I think it's a very nice result to show. Of course, this is still a quite intrusive, quite big, lumpy thing. But if you integrate it perhaps a little bit at the edge or make it optimize a bit the shape of it and the size of it, then you can make a nice-looking window, which could perhaps look like this. Additional benefit that he thought was if you make a panel like this opening up, then you have a better airflow through your room. So that you make more use of the airflow through via the ceiling of your room. Yes, I see what you're pointing at. This is a bit strange to have an openable, but okay. So next, third option would be shape memory alloy actuation. We also looked at that with another student. And this is a shape memory alloy, not by us, but by others. So if you heat up this, this metal, then it comes back to its original memory shape. So you can do this nice paperclip, or you can do this. So we thought, okay, if you have a similar metal like this, perhaps we can actuate the glass. We took a little bit simpler version, which is similar to this. So you have a wire, if you heat it up, it shrinks, let's say, and then you can lift this basket. So with this concept in mind, we developed a first system. We use this flexinol wire. It's a 0.5 millimeter thick wire, as you can see here. If you heat that up, it can lift about 3.5 kilos. And we heat it up by electricity. I think you need about 100 degrees there. But only 10 volts and some ampere there. And then, yeah, it's not a great video, but here you see the wire. This is 3.5 kilos. It lifts it up, and it moves with a stroke of about 3 to 5% in its length. So using that, she looked at different options how to use this shape memory wire in a facade system. So all kinds of options with, in red you see the wires there. Just to be able to bend the glass by pulling the glass inwards or outwards, or as you wish. In the end, we went first for this option, where we have two pieces of glass with a wire in the middle. You can see a first mock-up here. So I will first explain it. So you have two pieces of glass on the outside, of thin glass, 0.5 millimeter in this case. In red, you see the shape memory alloy wire there, which has some extra length there to create a longer stroke of the whole wire. So there's an extra circuit, let's say. And then if we heat up this wire with electricity, then it will pull this bar upwards, and then the glass opens up like this. And you can see it on the video on the right. It's a bit difficult to see perhaps, but this is then the glass opening up. You see the wire here in the middle, very thin. And if you switch off the electricity, then the glass is elastically, of course, returning and elongating the wire in the middle again. So it's a system that closes itself if the electricity is turned off. And she made some renderings of how you could use this, perhaps for an inner facade to an atrium, to be able to have openable windows for ventilation, or to make a facade on the outside that you have a double skin facade again, which can open up for ventilation or other purposes. I didn't include it in this presentation, but yet another student looked at, okay, how can we prevent that the glass deflects too much in a closed condition, because it's still thin glass, of course. So we looked at, okay, perhaps we have to pre-stress the glass, but the most viable solution would be to have some sort of magnet around the edge of the glass, like a refrigerator door, that if it closes up, then it seals again, and it finds some force there again by having the magnet already around the glass, which can also be a switchable magnet, perhaps that you switch it off if you need the glass to open up. And then the second, let's say, general concept that we looked at was thin glass composites. So can we make thin glass panels by combining it with other materials? First, we looked at closed cell configuration, so make a sandwich core, sorry, core with 2 pieces of glass glued to it, like a honeycomb, for instance. But quickly already looked at, okay, let's make an open cell configuration, like a sort of truss shaped core that we can print in between the glass and then glue the glass to that. So another student looked at, okay, how can we make such a core? This is the design that he made. So like pyramidically shaped core with these kinds of dimensions so that you can integrate it in an IGU size, let's say. And then we 3D printed it from a PET-G material. Quite simple printer technique that you use for that. And then by printing this truss core, we glue 2 pieces of 0.5 millimeter chemically strengthened glass to it. And then you have this panel with a specific, of course, appearance and specific transparency. So it's not necessarily intended to be fully transparent. The idea is, of course, that the core makes the glass stiff, so that you have a very stiff panel, but at the same time, a very lightweight panel, because the glass is very thin still. The core is also very lightweight itself. And also the panel is insulating, because it's a double layer panel with a cavity in between that could give you your insulating performance. We tested it with a simple 3-point bending test. So this is a very small panel, A4 size. Okay, just as a first attempt. We also made some analytical prediction, and that fitted quite well. So that, well, we're happy about that, of course. He also looked at, okay, what can we do with more translucent cores? So make a core which is fully printed, let's say. And then we looked at hyper-shaped cores, so a panel like this. He designed it like this. So this is the fragment size there. We also made some perforations to let some more light through the glass, so direct light instead of only translucency. And then we printed this again, so now in another direction. So you print this hyper core in layers, again PET-G, and then we glue it in between 2 pieces of glass, thin glass, 0.5 millimeter again, and then you have this kind of appearance on your glass panel. Again, a very small panel, A4 sized. We tested it again. Unfortunately, in this case, we didn't predict it very well, but that was because the adhesive failed a little bit. We had 2 less surfaces to glue to, so this was, from that side, not a successful test, but nice to be able to produce such a specimen. Yes. And then the next try was to look, okay, can we more optimize the core pattern? So can we make more use of the 3D printing opportunities to make differentiation in the panel? Because printing, you can print any shape you like, of course. So we thought, okay, perhaps we should make a more structural optimization using Voronoi patterns and densifying the pattern where you need it for structural purposes more, and leaving it open in the middle more for the view through your panel. So we made a specific script to come from a very regular pattern to, in the end, Voronoi pattern, open cell pattern that we could print. And then we made this kind of smaller samples again, about 30 centimeter long, in which you can see different patterns which are, to a certain sense, optimized for structural performance. But you see differences in transparency or differences in cell size to open up your panel for view through the panel, and more densification where you perhaps want to take more shear forces. With that, he made a first, let's say, case study design for a small building that we have at the campus in TU Delft. So replacing the whole roof with a glass panel with all kinds of different prints behind or integrated in that panel. This is a rendering of it. Of course, you can imagine that this is still quite a 2D configuration, so it's still, perhaps I can show it there. I mean, you can still also laser cut it from a solid piece of polymer. So what would be a next step is also to make use of more the 3D printing possibilities to make, for instance, inclined surfaces, so that you don't have only straight surfaces, but that you incline it also for daylighting, reflection perhaps, or shading performances that you might want to integrate in this kind of panels. And then the next step would be to look at curved surfaces, so make a 3D printed curved core. These are just some first attempts again. What can we do with warping the glass a little bit? These are some further attempts again with the trussed core. So this trussed core is printed really in this curved shape. For that, you need a lot of support material that you also need to print, and you have to cut it away later. So material efficiency is low, I would say, for this kind of production technique. But you could also imagine that you first shape a surface on which you will print your core later, so that you don't have to cut away a lot of material. Again, this was done cold bent glass, 0.5 millimeter, glued on top of this core material. And this was another attempt by a different student. In this case, we printed the core flat condition, and then we curved it by heating up the core at a high temperature, and then let it gravity bend into the right shape, cool it down, and then later glue the thin pieces of glass to it. Next steps would be to look at durability. So what's the durability of the core that we use? For the moment, we use PETG, which is not so UV stable material, I think. We did some initial tests with UV lamps on such panels, and also UV lamps on such, let's say, dumbbell specimens. And we discovered that you get a much more brittle response of the material of the core. To what extent that would be unsafe, it's not yet clear. But we can see that there is an effect on that, so perhaps we need other materials to print the core. Another step would also be to look into the insulating performance of such a panel, which students are now looking at. So this is just that you can see the effect of different patterns behind the glass and the heat flux through the glass, or through the core actually. Because now you make, of course, if you print something in between your glass, you make a connection, direct connection between the two pieces of glass, which give you the thermal bridge, of course. So that would be a negative effect on the insulating performance of your glass. And we're now looking into what extent this negative effect is, and if we can perhaps improve it. So we're doing some testing on this climatic box, small climatic box at TU Delft, where a small panel is then integrated here. Inside you have a specific temperature, outside we have a specific condition, and we are measuring with this red piece, we are measuring the heat flux through the glass panel there. And some first ideas of a student that graduated yesterday or Wednesday was to make a multi-layer glass panel like this, so that you go from a single layer, or so single cavity to a triple cavity, for instance, and that you shift the cores in between so that there is no direct thermal bridge through the whole glass panel. And this apparently helped quite a lot in this insulating performance there. So just to give you a very brief summary, I think, well, I just showed you some concepts. It's not yet at the building scale, but I think it offers interesting opportunities for applying thin glass in either adaptive systems or composite systems. What should be done next is really upscaling, so making bigger panels to show the feasibility of it. Lamination is very important, of course, also as addressed by Marco. This was all unlaminated glass, so fairly easy, I would say. But especially for the bendable panels, we have to look at very flexible interlayers that can still provide enough post-breakage safety, actually. And of course, we have to look at the durability of the whole system, the materials that we use, how are they affected by, for instance, UV and other climatic exposures. I certainly did that not alone. There's a lot of students involved here over the last 2 years, I guess, and also a lot of co-supervisors of these master thesis projects. So great acknowledgement to all of them. And certainly also an acknowledgement to the support of AGC and also Marco to provide us the samples and the technical support for doing this kind of studies. Well, as introduced, I moved to Dresden, so just would like to show this is our group in Dresden. If you're around, you're certainly welcome to visit us. If you want to do it digitally, you're also welcome to visit us. But yeah, if you're close or in the neighborhood of Dresden, please give a call and we show the lab. And the last advertisement I would like to make is for the Challenging Glass conference. We are organizing that again in June next year. 18 and 19 June in Ghent University, hosted by Professor Jan Belis. And also together with Freek Bos from TU Eindhoven, we are organizing that next year. So if you would like to attend, or would like to present, or would like to sponsor, that would also be very nice. Please come to us and we can discuss all the options. Okay, thank you very much.
Christian, very much. Thank you very much for this very inspiring presentation. Is there a question from the audience? I think the audience look for the happy hour and the farewell party today.
On the left, you can.
Oh, there's one. Sorry.
Thank you. Could you say something about the weight of glass? Bucky Fuller spoke about the weight of buildings. And in terms of, if you think about eyeglasses, the very highly dense, optically optimal eyeglasses, they are heavy in comparison with those that are made out of the plastic glasses, the acrylic, the composite materials. So if we think about thin glass, is it actually becoming heavier? Or
no, I think I have to double check, but the density of, let's say, normal window glass, cellular silicate glass, and aluminosilicate glass, which is this, that's not big of a difference. The gain is really in the thickness reduction that you do. So typically you would apply, let's say, 4 or 5 millimeters of glass in a window, and now you would be able to reduce it to 0.5 millimeter. So there you get your benefit in the end. So the material itself is not lighter on sich.
But so basically the benefit is really huge, because there's also the problem today with the soil, so with those buildings that may be sinking in clay. So basically, Shanghai is no longer. I read an article about Hong Kong, Shanghai, California, basically sinking down because of just the climate change, flooding, different weather conditions. So if the buildings are becoming less in their weight, the benefit is huge.
Yes, I agree. But I think you cannot completely solve it only by the glass in this case. I mean, there might be other opportunities also to make it lighter, the building. But if it helps, yes, it certainly helps. And in the end, I think also what Marco pointed out in the previous presentation, like if you make a panel of 50 kilo, the benefit is more in the handling also, and the transport and the installation, so that you can indeed lift it by 2 persons. But the secondary benefit is indeed that also the building becomes lighter.
Yeah, there's another question in the background.
How susceptible is this glass to, say, normal window washing operations?
If it's more or less than normal glass, perhaps you have an idea?
Yes.
Yeah, go ahead.
Can you repeat the question, sir?
How susceptible is this glass to damage from, say, normal window washing operations?
No, no more than normal actually, because you have a pre-compression normally, so you start from a situation which is better than normal glass. So no, I do not see that as a problem. I thought the
pre-compression zone is thinner, right? Than,
yes,
say, heat-treated glass.
It's thinner, but is thick enough for these sort of operations. Because you can get up to 80 microns after chemical tempering, which is test has been done with sand abrasion, so artificial aging, and that's fairly enough for this sort of application. I would say even more severe scratch will resist to that. Although tests need to be done. Thank you.
Is there another question?
No, happy hour started, so.
It's happy hour time. I think so. Weird. Okay, thank you very much.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.